Hello, everyone. Thank you for attending this talk. My name is Sadegh Riazi. I'm the founder and CEO of CipherMode Labs. It's my great pleasure to talk about our technology and how we can empower the defense sector. This talk has five major parts. In the first part, I will talk about the grand challenge of data security versus data utilization. Then I will talk about why current technologies are unable to address this challenge. I will provide an overview of the competing technologies. And at the end, I will provide a detailed description of what we are doing here at CipherMode. You will see how this technology can unlock the full potential of data and provide unprecedented opportunities. At the bottom of this presentation, you can see the progress as we move on into the presentation. Before jumping into the technology, it's important to observe what makes a superpower a superpower. It used to be the land that determined who has the most power and resources. But during the Industrial Revolution, land gave its role to machines. Industrial countries were able to control most of the world, mostly because of their superior machinery. In upcoming years and decades, it will be data that determines the superpower. The quality of the data, as well as the ability to process large volume of data, will be the differentiating factors. In practice, there are many obstacles in unlocking the full potential of data. For instance, when banks try to identify money laundering activities, oftentimes it's very challenging if they only have access to one database. Running the algorithm on each database may not detect the target activity. In contrast, if they were able to aggregate the data and leverage the aggregated database and run the algorithm on all of these three databases, they may be able to understand this interbank fraudulent activity much more effectively. In general, whether across different countries or within a country, there are many scenarios that multiple entities are interested to perform a joint computation. An obvious solution would be to give the data to a trusted third party to perform the computation for them. In practice, it's very challenging to find a party that is trusted by all entities. Not only is this hard across different organizations, it's also very challenging to access data that belongs to a single organization, but data resides in different jurisdictions. Aggregating the data can be against the laws and may cause a company to be fined later on. The fundamental dilemma is due to two opposing forces in this context. On the one hand, we are interested to collect more data and leverage artificial intelligence to extract valuable information from the data. On the other hand, there are critical concerns revolving around data security and privacy. As famously put by Dr. Andrew Ng, we know that it's not who has the best algorithm that wins, it's who has the most data. We also know that protecting data is an increasingly challenging task, and we need to protect our data. Traditionally, it was assumed that we only have two options: either keep the data unprotected in plain text or clear text format and allow any computation to be performed on the data. Or we have the other option where we can encrypt the data, make it unintelligible, and keep it secure, but have no ability to extract any value from it. If you put it in this two-dimensional chart, you can see that plain text data or clear text data resides here. It has the highest utility, and this is the easiest way to leverage data, but at the same time, it has the lowest level of security. Encrypted data or ciphertext resides here. It has the highest level of security, but at the same time, it provides almost no utility for us. The ideal solution sits somewhere here, where we have security guarantees comparable to encrypted data and data utilization comparable to plain text data. And this is what we are looking for. Using modern cryptography, we are able to securely transfer data from one location to another, while we only have access to an untrusted communication channel, such as internet. where there can be many adversaries listening to the information, the traffic of the data. The way that we can accomplish this is that we can use encryption and a secret key to encrypt the input data and make an unintelligible version of it. Then we can transfer this new version of data over the internet, where we can reconstruct and retrieve the original data using the same secret key. Once we have that, we can do any type of computation that we are interested to do. For example, in this case, we are running an AI model on the MRI image. Once the computation is finished, we can send the report back using the same mechanism to the entity number 1 on the left. However, as you can see in this computational model, which is ubiquitous today, the entity number 2 has direct and unrestricted access to the input and output of this computation, where the data belongs to the other entity number 1. And if the company is compromised for any internal or external factors, the data is directly revealed to the attacker. In terms of terminology, we call the data in clear text or in regular format plain text, where you can extract valuable information from it. The ciphertext is the version of the data that reveals no information about the original plain text data. What we are interested to do and what we offer at CipherMode is a way to directly compute on ciphertext without ever decrypting it. This way you can see that the secret key only resides with the entity number 1 and is never disclosed to the other entity. Yet we are able to do the computation on the data as accurate as we could do in plain text version. There are a handful of technologies that provide data security and utilization at the same time. They have different trade-offs though. The first category is called fully homomorphic encryption. The major shortcoming of this approach is that it can only evaluate polynomial functions, which is a very limited set of all possible functions that we are interested to do. The second category is called trusted execution environments, such as Intel SGX or ARM Trust Zone. The major shortcoming of this approach is that because this is a hardware-based security approach, it has a very limited secure memory that we can leverage during the secure computation. On top of that, there are several well-known side channel attacks using power side channel or timing side channel that they can extract valuable information about the secret data using other processes that are happening on the same hardware platform. In CipherMode, the technology that we offer can support any type of functions that we are interested to do. Moreover, we have a systematic approach for integration where the final product and the application at hand does not change the security parameters that we need to tune. This is in contrast to homomorphic encryption, where the encryption parameters depend on a specific application that we are targeting. And this can be the source of many vulnerabilities. Going back to this two-dimensional chart, we can see that the homomorphic encryption sits here. It has much higher data security compared to plain text, but has a lower utility because we cannot do any type of computation that we are interested to do and encrypt the data. To the right, there are trusted execution environments such as Intel SGX, where they have lower security guarantees compared to homomorphic encryption, but they have higher utility. You might also have heard about differential privacy, where they offer a different security guarantees. Roughly speaking, differential privacy is a way of adding specific kinds of noise to a database such that the statistical properties of the database are preserved and we can do statistical queries, but we leak lower information about individual records. What we're interested to do is that we want to do exact computation on any individual data record, and we want to keep the data fully confidential. And this is the focus of what we're doing at CipherMode. We provide same security guarantees as standard encryption schemes, while allowing arbitrary computation on plain text data, as we will get into more details in the upcoming slides. At a high level, what Internet provided for us was connectivity, an infrastructure that anyone can transfer information to any other person. At CipherMode, our vision is to build a secure computation platform that sits on top of the Internet, a platform that allows everyone to extract value from data without compromising confidentiality. Let's dive deep into the technology and see how these promises can be realized. Here's a very simple example where we are interested to do secure addition and multiplication by a constant number. We have three parties. Alice sits on top. We have Bob in the right bottom corner. Alice holds secret variable x with value 14. Bob has secret variable y with a value 23. What all parties are interested to do is that they want to compute this simple function. They want to do the summation of these two numbers multiplied by 2. But we have other constraints. We do not want to reveal x, y, and the result of the computation to any other party. The way to realize this is that Alice creates a random number, and it creates the second share such that the summation of these two shares correspond to the original secret value. It's worth noting that none of these two shares reveal any direct information about the secret value by themselves. The combination of them would reveal the secret value. Bob also does the same task. It creates two shares. Alice and Bob distribute these shares to the other parties. And once each party has its own share, they locally compute a summation on these shares. In real computation, if you can see, the summation of these two secret values would be the summation of these two shares. But none of the parties know the final result because none of the parties hold two of the shares. If we continue by multiplying the shares by a constant factor 2, they will end up with purple shares, which again, thinking about the real computation that is happening, you can see that the summation of these two shares equal the result of this computation that we were interested to do. So as you can see, we were able to do this computation without revealing any information about each part of the computation to any other party. At the end, these two parties are holding a secret share of the final result. And we can do this type of computation as long as we are only interested in doing secure addition and multiplication by constant. Moving to other operations such as comparison, the task is significantly more complicated. If we are interested to compare these two numbers and identify which one is bigger without revealing this information to any other party, this is a very challenging task. One heuristic solution might be to ask each party, is your number bigger than 100? If the answer is no, we continue a path similar to binary search until we find the answer that yes, there's a number that is bigger than one of the numbers that we asked, but the other share is not. However, in this example, Alice gets to know that the other number was somewhere between 17 and 25. And this is a lot of information revealed indirectly to Alice. In our constrained environment, we do not want to reveal any information about each of the data, but we are interested to find this answer. In case of secure comparison, this was an open problem in computer science until 1982, where Dr. Andrew Yao proposed the first solution in his seminal work. In the previous two slides, we saw two examples for two relatively simple computations, one with the simple answer and one with a complicated answer. In general, if you want to support any type of applications, the task is significantly more complex, and it has a 4-layer structure to be able to support any type of applications. At the far bottom layer, we have fundamental cryptographic tools, such as public key encryption, symmetric key encryption, and one-time path. Building on top of these fundamental tools, we have intermediate protocols, such as oblivious transfer and zero-knowledge proofs. On top of that, we have high-level protocols such as Yaw's garble circuit. And in order to benefit from these protocols, we need to transform the input function to a representation that is known as circuit description to be compatible with these protocols. Either describe them as series of Boolean logics or arithmetic gates. Our strategy in CipherMode is to stand on the shoulder of giants. There have been more than 3 decades of research by some of the most brilliant computer scientists of our time. To put this into perspective, the entire field of deep learning has received 1 Turing Award, which is considered the Nobel Prize in computer science. In this area, though, 3 Turing Awards have been given to computer scientists that have solved fundamental problems in each of these layers. Since then, the challenge has always been the connection between these layers, as each of these building blocks incur enormous computational overhead and make the overall solution from application to the bottom very impractical. This is why at CipherMode we have had several breakthroughs reducing the overall overhead by more than 3 orders of magnitude. We have had theoretical breakthroughs where we described how we can map the circuits to these protocols. We have designed new protocols that are customized for specific operations. Last but not least, we have had system-level breakthroughs that provide superior concrete performance overall. For the sake of time, I'll only talk about the first 2 layers. At the circuit description layer, the first step is to express the application that we are interested to do as a series of logic gates or arithmetic gates. However, even for simple operations such as multiplication, the most optimized construction is unknown. Different circuits lead to different complexity and concrete cost. In general, creating the optimized circuit is an NP-hard problem for which an efficient algorithm does not exist to this date. At CipherMode, we have designed new tools that create significantly more optimized circuits compared to prior-based solutions and reduce the overall computational overhead in the secure computation protocols. In the next layer, we need to process each gate type using a specific customized protocols that we have designed. And in order to reduce the overhead again, we compute each of these gate types in a specific protocol, and we do secret conversions securely along the way. Now we can talk about CipherMode solutions. We have 3 lines of solutions. The first one is called Neural Cipher, which is a platform for secure neural network training and inference. And we will see some examples in upcoming slides. The second product is called Cipher Colab. It's a secure collaboration platform where multiple parties can jointly compute any function. For example, they can run SQL queries on an encrypted database. Last but not least, our latest product is called Cypherium, which is the first of its kind general purpose processor, which is able to do arbitrary type of computations and accepts high-level programming languages such as C++ and Python. Here's an example of Neural Cipher use case, which is currently the fastest secure neural network solutions out there. In this case, there are 2 agencies that are interested to do this joint computation. One holds raw data and needs the report where the raw data being processed by the AI model held by the other party. However, none of the parties are willing to share their data. In this case, they can use Neural Cipher. The first party encrypts the data, sends the encrypted data to the agency number 2, where they hold an already trained neural network using in popular machine learning frameworks such as TensorFlow or PyTorch. Once you have this, you can seamlessly run this encrypted data using these frameworks and return the encrypted result back to the agency number 1, where it can decrypt and identify the result. In this computation, the AI model is not revealed to agency number 1, and input and output of this computation is not revealed to agency number 2. In terms of concrete performance, compared to Microsoft Research CryptoNets technology, which is based on homomorphic encryption, they require 300 seconds to perform single inference on any dataset. The result was later improved using other type of secure computation protocols by Visa Research, and they reduced the overhead to 5 seconds. At CipherMode, we are able to complete the identical task in identical security model in only 150 milliseconds. It's worth noting that as the number of layers in the neural network increases, naturally our computational costs in CipherMode increase, but it increases linearly. If you run the same task using homomorphic encryption, the computational overhead increases exponentially, at which point where there is a threshold of 9 layers, the computation becomes impractical. And as you know, all of the state-of-the-art neural networks reside on the right-hand side of this threshold. For example, for famous image classification challenge, there is a popular network called ResNet, which has 34 blocks, and each block has 3 layers. And as you can see, this is far beyond the capability of homomorphic encryption. However, in Neural Cipher, we are able to support all these standard benchmarks. This is why we were first to support AI-based healthcare diagnosis. Hospitals can encrypt their patients' data and send it to any AI company for the data to be processed without hospitals violating privacy laws such as HIPAA. The AI company does not get to learn anything about the patient's data, yet they will be able to do the computation for them. We run our Neural Cipher engine on 4 medical datasets for malaria infection, liver disease, diabetes, and breast cancer. And as you can see, the inference time is in a practical regime of less than half a second and less than 100 milliseconds in 3 of the cases. And it requires very limited communication and achieves very high accuracy, as high as 97%. The second line of product is called Cipher Collab. It's a platform for secure collaboration. And as we saw in the beginning of this presentation, this can be used for anti-money laundering detection, where 3 financial institutions can work cooperatively and identify the fraudulent transaction without revealing anything else about the rest of the transactional data. We can also use Cipher Collab for secure SQL queries on encrypted databases. Last but not least, we have Cypherium, which is the first practical secure CPU. And the significance of this product is that it allows any software developer with no cryptographic background to use Cypherium to run arbitrary computations on encrypted data written in high-level programming languages such as C++ and Python. Given these arbitrary programs, 2 parties, in this case, 2 parties are interested to run this program on their datasets. And they can use Cypherium software to execute this program on the aggregation of these 2 datasets without revealing anything about their datasets to each other. The entire traffic here is encrypted end-to-end. With that, I'm happy to answer any question. Here we are available to address any challenge that you have in your organization that requires utilizing data, but there are severe security and privacy concerns. We are happy to help you integrate. We are also looking for security researchers and engineers. If you're interested to contribute to this technology, please reach out to us. We will also be available at Ridgewest virtual booth at 11 a.m. Thank you for your attention, and I'm happy to answer any questions.